So today we'll wrap up chapter 4, and then we'll have some clicker questions. So last class I asked tough clicker questions. I'm gonna ask tough hard clicker questions here also, and I'm gonna purposely I put tricky clicker questions and whatnot. Because I think they serve as a good place to discuss tough topics and force you to kind of think and remember, and that way, they're important concepts that when we cover on, that I feel like should be covered on the exam, and I feel like by giving you exposure in class where the stakes are low, it's okay where you guys get them right or wrong. And that way, when the stakes are higher on the exam, it won't be the first time you see them, and I won't feel like I'm totally just setting you up for traps. Okay, so I am. So you might get the sense that I've set you up for traps and whatnot during today's clicker questions. Slightly intentional, but it's also think of it as practice, right? We practice so that during actual time you do well. Okay, so let's wrap up chapter 4, and we're going to start with the discussion of R. So we have correlation. Correlation is equal to R, and for linear regression, okay, if we square R, okay, we get R squared, which takes on a special thing, big R squared, okay? And so big R squared, this is known as the coefficient of determination. All right. The coefficient of determination is can be defined as the amount of the variation in y that is explained by the variation in x. Okay, so let me kind of illustrate or try to explain what I mean by that. Okay, so let's say we have x and we have y. Okay. And let's say we're looking at some, I don't know, cows or something, okay, young cows. X will be their age, and Y will be the weight. Okay, and so, while the cows are young, we might see a linear relationship between age and weight, okay? Once the cows reach maturity, they're probably not going to be continuing to gain weight. This levels off at some point, okay? But as far as the young cows go, we might see some kind of linear relationship. Okay. And so here, with something like this, perhaps R is equal to 0.9, and that means R squared is 0.81. Okay, and so what this R squared means is that, if you think about what goes into determining the weight of a cow, there are lots of things that could determine the weight of a cow, okay? It could be, age is going to be one of them, but it could also be diet, you know, how much the cow is eating, how much exercise the cow's getting, genetic factors, maybe the cow is coming from a long line of very big cows, or I don't know, whatever this is, okay? So there's lots of factors going into determining cow weight, okay? Okay, so maybe age, but diet, genetics, etc. Okay? And what we're saying is that the inclusion of age, with X being age, age can account for about 81% of a cow's weight, okay? So, you know, cows weigh different amounts and things like that. About 81% of that variation can be accounted for by age. We're saying about a cow's weight can be explained by age. Okay, so this is kind of the concept of the coefficient of determination as far as that goes. Let me let's see. So this is Stats 10, Lecture 4, Week 3, Friday. Okay, let me just apologize. Let me just okay, is that good with you all? All right, so this is r squared. It's the coefficient of determination. We would just take our value r and we would square it, okay? Okay, so let's, so I'm going to draw a little picture here. Okay, so we'll say you perform a linear regression analysis between x and y. Okay, and you find that 49% of the variation in x, variation in y can be explained by x. All right, so we'll say estimate r. Okay. All right. Okay. So I'm going to say 0.51. 0.9, 0.7. Okay, so go ahead. You can pull out your clickers and you can click away in terms of your estimates of Okay, so we'll say 5 more seconds to get your clicks in. So 5, 4, 3, 2, 1. Click, click, click. Okay. All right, and our correct answer is the letter D. Okay. So here, so 49% of the variation in y can be explained by x. We would say r squared is 0.49. Something. Okay, and so r will be the square root of 0.49, which means it can either be plus 0.7 or minus 0.7. So based on our negative trend here, we choose minus 0.7. Okay. Good? Yeah, I still can't believe Kobe's not going to play anymore. Sometimes I think about that. That was such an epic game, though. Oh my gosh. Oh my gosh. You guys missed out if you didn't watch it. All right. What was I talking about? Kobe. And Steph Curry with his 402 3-pointers. Also crazy. All right. All right, so I have to now talk about warnings about linear regression. So the real question is, can the Warriors get past the Spurs, right? Like that's I feel like that's the true. If they can beat the Spurs, then whatever. Toronto, Cleveland, no worries. Okay. Sorry, LeBron. All right, warnings about linear regression. Okay, so number one, make sure the relationship between x and y is linear. Okay. How can we tell if x and y have a linear relationship? Okay, so what's that? Yeah, we must make a scatter plot and look at it. Okay. R by itself cannot tell us if the relationship is linear. Okay. So make sure that's the case before you do linear regression. Okay. Another warning. Okay. I'm just drawing a blank here. So, okay. Okay. Oh, beware of outliers. As they can greatly affect your analysis. Okay, so let's say we were gonna, here, I'm gonna just flip over to the next slide. Okay, so this will be watch out for outliers. So you don't have to write that again. Okay. Let's say we were going to look at the relationship between income and pizza consumption. Okay, so we ask people, how many pounds of pizza did you eat over the year? I don't know, maybe pounds is not. How many times did you eat pizza this past year? Okay, and then we ask, how much money do you have? Okay, and what kind of relationship would we expect to see between income and pizza consumption? Like how much pizza someone eats and how much money they make. Are we expecting to see any kind of relationship? Or yes, no, maybe? I'm expecting like almost no relationship. I'm expecting to see people with high income, some of them eating lots of pizza, some of them eating little pizza. People with low income, some of them eating lots of pizza, some of them eating little pizza. Maybe down at the extreme levels where you have like almost no income, people are maybe perhaps too poor to eat pizza. But overall, I think, overall probably not a huge trend between pizza consumption and income levels, okay? So if this is what we would see, oops, that's not the color I wanted. I wanted this. I would expect to see kind of like no relationship, right? No relationship, our trend line would be flat, okay? Okay. Now what if in our analysis, let me just move this out of the way. I surveyed Papa John, okay? So this is going to be Papa John. I'm assuming he eats lots of pizza. I don't know, okay? And he's rich, right? So he makes lots of money because he owns Papa John's, the franchise, and I'm assuming he's going to eat lots of pizza. Or maybe he doesn't. Maybe he hates the product he sells. But I'm going to assume, okay, if this were the case, our trend line is now going to try to fit Papa John, okay? And then we would get something like this, right? And then so now our trend line shows a positive relationship between income and pizza consumption. Okay, and so this we don't want. This may not necessarily be something we want. Okay, and so what we're going to do is if you see outliers, if you have outliers, okay, you should investigate, look into them. Okay, look to see what they are. Okay, they could be errors. They could be just someone accidentally hitting a couple extra zeros, saying, "Oh, I ate pizza 10 times this past year," and then I accidentally hit a couple extra zeros. "Oh, I ate pizza 1,000 times this past year." That's a lot of pizza, right? So I don't know. I'm trying to, okay, when I was in college, I ate pizza like every week, maybe perhaps multiple times. Okay, I'm not proud of that, but now today I eat McDonald's way too much. We're lucky that we don't have McDonald's on campus because I'd be going there all the time. I go to Jamba Juice way too much also. I don't know why I'm telling you this. All right. So if you have outliers, look to see what they are. Okay, they could be errors, and in that case, remove them. okay? They could be errors, or they could just be unusual points, okay? And you should never just throw away outliers just because they're inconvenient. Okay, so don't just throw them away just because they're inconvenient. You should always, you can remove them, but you should have a good reason, right? If we say, okay, you know what, Papa John, you don't really represent the rest, you're in the 1%, so we don't want to include you in our analysis. Okay, that's fine. You can say, I'm just curious about pizza consumption for quote, typical income earners and things like that. Okay, so they could be unusual points. Okay, you can choose to do two analyses. One with and one without the outliers. Okay. All right. Is that also okay? Okay, and then the next warning is do not extrapolate. Okay, so do not make predictions where we have not collected data. Okay, and so in this case, so here I'll just do a silly example of something you don't want to do. All right, so let's say you have a kid, okay? So, and and you decide to start measuring his height maybe at age 3, okay? So on the x-axis we've got age, and then we're going to measure the kid's height. Okay, so at 3 years old, he's this tall, and then the next year he's this tall, and you measure the kid's height every year. And like maybe even multiple times a year, okay? And so by the time he's 10 years old, you see a very strong linear relationship between age and height, okay? So you have a strong linear relationship, and you say, oh, well, I can fit a linear regression model, okay? And based on this, by the time he's 55, he'll be 22 feet tall or something like that, right? Okay, so at age 55 he will be super tall. Okay, and we know that's silly, right? We know if we looked at growth, sure, in the beginning you grow steadily, okay? That's why every time you go visit your grandparents, they're like, oh, you've grown, look how tall you are. Or maybe they don't say that. But then around age, 17, 18, 20, some of us 14, we stop growing, right? We kind of get, and maybe at an old age we decline a little bit, okay? So the truth is it's kind of something like this, right? And so it is incorrect to assume, so even though we see strong linear pattern between, the early years of childhood, it would be incorrect to assume that this continues throughout life, okay? So linear trend exists, it is incorrect to assume this will continue forever. Okay, and so you know, it's silly to do this when we're talking about age and height, okay, because we know that that's not how the world works. But very often you see people trying to do this in other situations. They say, oh, for the past, you know, 20 years, we've seen this kind of growth pattern, okay? And then they assume, okay, and they say like, oh, if this continues on, then in the year 2050, it'll, you know, the world or whatever will look like this, okay? And the truth is we really don't know what's going to happen in the future, okay? So I'm going to just draw a little picture, you know. So we could see something like this, okay? And this could be now, all right? Now, but as far as what happens into the future, so if this is now, as far as the future goes, sure, it could continue like that, but it could go like that. It could go like that. It could even go like that. We have no idea, okay? So no one knows what happens in the future, all right? That's, if no one has told you that, then I'm telling you now, okay? No one can predict the future. With any certainty. Okay, so patterns can exist in the past, and sure, linear regression is very useful if you want to be like, oh, what, you know, how tall would we predict for something around here? Sure, fine. Predicting things far in advance, very, very hard to do, okay? You know, we can kind of predict a little bit into the future, just a little bit, you know, maybe depending on what we're talking about, maybe a few hours into the future. If we're talking about the weather, we can usually predict that pretty well. But as far as weather goes, we can generally predict with accuracy, maybe just like 1 or 2 days in advance, okay? Beyond 2 days, like as good as we hope for the weather, it's really not that great, okay? You know, we have weekly forecasts, but those are, you know, beyond the second or third day, it's really just a guess and crossing fingers. You know, with politics, we have no idea what's going to happen, right? If any of us looked at the political landscape 6 months ago, okay, we would have no idea that this is where we are today. So lots of stuff, you know, okay? We don't, it's hard, okay? And so anyway, don't extrapolate. And it's very tempting to do that, okay? Because you create this nice model and you're like, oh, well, I'm just going to plug in these values out here. Okay, let's, so now I'm going to ask you a series of clicker questions, and we'll see how we do, okay? Just kind of wrapping all of this stuff up here. Okay, so that kind of wraps up chapter 4. Let's see. So you have a midterm 1 week from today, next Friday, and that will cover chapters 1 through 4. Next week I'll start chapter 5, but chapter 5 will not be on the midterm. It'll be on the quiz during week 5. Okay, so, all right, so here's a question, clicker question. Okay, so we'll say you create a linear regression model, model or analysis for X and Y. Okay. You compare the actual value of one of your data points to its prediction. Okay, so in this, a negative residual means, dun 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 dun, okay, all right, here are your answer choices. Okay, that the data point is missing in our analysis. Okay. Predicted value. This is minimum. Okay, so what does the negative residual mean? Oh, I gotta start the clicker. Sorry, I apologize. Okay, go ahead and click away. All right, look at that number climb. Everyone's still doing okay in terms of schoolwork? Third week, everyone's doing all right? No? I'm seeing head shaking? Oh, man. Okay, well, I'm sorry to hear that. I hope this class hasn't been too much of a burden. No, okay. Well, I try not to make the class too burdensome. All right, well, I'm going to click stop in just a few seconds here, so get your clicks in. Click, 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 and stop. Okay, let's see how you guys responded. Is this working? Oh, here we are. Okay, and that's correct. Answer choice C. The predicted value is larger than the actual value because a residual is actual minus predicted. So if we're getting something negative, then that means the predicted value is larger. Okay, so we might say E is Y minus Y hat. Okay. All right. Well, whatever classes are giving you trouble, hang in there and try to get plenty of rest. It's I know it's like, who are you to tell me to sleep? But it really I just listened to this thing on like how sleep works in the brain, and apparently as you are awake, because they were like, you know, why do we even need to sleep, right? So apparently as you are awake, your brain builds up little toxic chemicals in your brain, and sleep flushes them away. And so if you don't get enough sleep, the next day you're gonna have all these still toxic buildup, and then you don't want it to be like never brushing your teeth. So imagine going to sleep as brushing your teeth, and so if you don't get sleep, you're not doing a good job brushing your teeth, and then you're gonna have nasty stuff in your brain. Oh well. Okay. Okay, so we'll do another one. We'll say you look at the relationship between x and y, okay? Oh, and y is Andy. You look at the relationship between x and y, the correlation is 0.95, okay? The x bar is 2, y bar is 5, standard deviation of x is 3, standard deviation of y is 2. Okay, so we're going to say true or false. So A being true, B being false. True or false? Okay. We should perform linear regression, and the slope of the line will be 0.6333. I think, let me just make sure. Yes, okay. All right. You can try this one out. So you can discuss with your friends. All right, so we'll say, I don't know, 10 more seconds to make a decision here. So get your clicks in. All right, so 5, 4, 3, 2, 1, and okay, let's take a look. Okay, and the correct answer is B. Okay, so what's going on here? All right, so the key here that is false is that we should perform. This part is false. Okay? So remember, when deciding whether you should perform linear regression or not, you need to make sure that the relationship between x and y is linear. And there's nothing here that says x and y have a linear relationship. Okay, it says correlation is 0.95, but this is does not mean it's linear, okay? Does not mean a linear relationship. Yeah, question. Yeah, it could be we can perform that. I guess that would be true. You can always do the wrong thing. If I had said somewhere in here a scatter plot shows a linear relationship, then that would make it true. Okay, so if it says a scatter plot shows a linear relationship, okay, then the statement would be true. Okay, so this was classic misdirection, right? Probably you guys were focused on the calculation of the slope being sy over sx. And indeed, this does come out to be 0.6333. Okay? But the key here is we should perform and we should not, without knowing if it's linear regression or linearly related or not. Yes?
Technically, in order to test if it's linear or not, don't you have to perform a linear regression test?
No, you have to create the scatter plot. You create the scatter plot, which is not linear regression. Linear regression is fitting the line.
But like, once you do the line, then you have to do a residual plot and see if it's random scatter on both sides of the residual plot to see if it's a linear regression.
Okay. I would say you can create a scatter plot, and from a scatter plot alone, you should be able to make a judgment call of whether it's linear or not. Okay? The point here is there was nothing here that said it was a linear relationship. Therefore, we can't jump to the conclusion that linear regression is important. Okay? And so, yeah, a little bit of a tricky question. You might see something like this on the midterm or something, but at least you'll now be aware that, hey, I got to check to make sure that the question says something about there being a linear relationship. Okay, last one. All right, so a scatter plot reveals that linear regression is appropriate. So we will say that this part is met, okay, and we'll say y hat is equal to 3 plus 4x, okay? So interpretation of the slope. Okay, and we're gonna, all right, so this is again true or false. Okay, so we will say interpretation of the slope is that increasing x by 1 causes an increase of 4 in y. Okay. So go ahead and click true or false. Okay, and I apologize that we'll go just a tiny bit past 250 here. Yes. I have it written the way I want it written, okay? Okay, so we'll say 10 more seconds to get your clicks in. Okay, so 5, 4, 3, 2, 1. Okay, the answer is false. Okay. All right, and let me explain. This is important. This is important. Okay. So the answer is false. Okay. The key here is it says causes. Okay. So regression says nothing about cause. Okay. Regression says nothing about cause. You could look at, income levels and educational or even academic performance, and you'll see some kind of positive correlation or positive regression line, but it doesn't mean that one is causing the other. Okay, an increase. So it would be correct to say increasing x by 1 is associated or is associated with an increase of 4 in our prediction of y. Okay, so the key here is that we are talking about the prediction here. So our regression line is always about the prediction of y and not y itself. Okay, so regression says nothing about cause, and then the line is always about y hat and not y itself. Okay, that's it. Have a good weekend. We'll see you guys on Monday.